Okay, thanks, Michael. Yeah, I will talk about a little bit about the differences between CircuitPython and MicroPython. Spoiler alert, there aren't a lot of big differences in the actual way the languages work. They both adhere as closely as they can to the canonical Python standard with adaptations that I guess make sense for the limited machine environment in which they run. There are a lot of differences, and some of them very favorable, depending on your application, in the way you get the way you get Python on the box and the way you manipulate it. So, and I'll show you CircuitPython, how that works, which is basically a drag and drop sort of scheme that Adafruit has implemented. And I'll show you a dedicated board that we used in our scavenger hunt at the Maker Faire, which is running MicroPython, not CircuitPython, but MicroPython on an ESP32, which is an inexpensive Chinese-made processor that is extremely popular as a successor to the 8266, which you may have heard of. So the nice thing about MicroPython or CircuitPython, either one, is that they allow you to do embedded development using a truly high-level language. Up until this point, embedded development was pretty much done in C or C++ or some combination thereof. That had very much to do with the extremely limited memory capability and speed capability of something like, say, an Arduino, which has maybe, I don't know, 32K of flash, that is code space, 2K of RAM, meaning there won't be large arrays of ints, and that's about it. So C and C++ are choices that make sense there, particularly on bare metal machines, because they enable you to make the most space economical code. Now, with the growth of the ARM-based machines, and I'm pretty sure that the Adafruit Circuit Playground Express is actually an ARM-based machine, and the ESP32, 8266 family of ARM-like processors. There's a lot more speed. So the ESP32 is running at 240 megahertz. Now, that's not blinding speed by PC standards, but it's blinding speed compared to 16 megahertz in, say, an Arduino. And they've got what looks like, to the embedded programmer, a lot of memory, say 256K of memory, which is enough to have to run a Python interpreter. I'll show you briefly, if I share my screen, I'll show you a little bit about each of CircuitPython, basically their page, MicroPython, and then I can show you a little bit about what happens, how you get code onto a CircuitPython Express, and then how you get code into a MicroPython-based machine like an ESP32. So I'm going to step through those things. And I have an application on the ESP32 machine that measures temperature and humidity and has a little web service. So it's non-trivial application. It's not hello world, it's not profound. So let me share my screen. Hopefully in a minute, when the video stabilizes, you'll see the, I'll start with CircuitPython. You'll see the CircuitPython web page. Circuit is a branch of MicroPython. It's officially branched, and they basically track MicroPython changes. I think MicroPython was the original development. I think it started as a Kickstarter out of Australia, and the original port was done by some Australians. Adafruit picked it up because Adafruit is a big vendor in the DIY embedded space, and they're an excellent vendor in the DIY embedded space. And they customized MicroPython primarily to port it to their own boards, because they have a wide variety of CircuitPython capable boards, and also to make it easier for beginners, that is those who are not used to the kind of esoteric tools that inhabit the embedded world, to connect to it. Because when you are working on a remote machine, a remote microcontroller, it's not local, so you have to be able to push code to it, pull code back from it, debug, and all those kind of things. And usually you have to do that over a serial connection, which, as you'll see, I'll show you that in MicroPython. It's kind of clunky, although Visual Studio Code makes it a lot easier. But what happened with CircuitPython was Adafruit thought, and they did, make it really easy. So what happens is they make the remote device, let's say it's one of these CPX Circuit Playground Express boards. They have other boards. It appears when you plug it in as if it were a thumb drive, a USB drive. So it appears as a new shared folder essentially on your desktop. that means that to put code on it, all you really have to do is to drag and drop code from wherever you have that code stored on your machine onto the shared drive, which is mapped by the CircuitPython board. And then it will start, if you name it the right thing, there's a magical code.py name, you have to name it, and it'll start to run. And then you can communicate to and from that board over the USB cable. So that's actually, that means, as they point out, that you can use any editor you want. They do supply an editor which is written in Python, and I forget the name of it, but it works pretty well. But you can also use Visual Studio Code. So Adafruit programmed basically, let me see if I can find a list of all the supported boards. They've got a lot of supported boards with CircuitPython. And mostly their own boards, because the Feather, the Trinket, the Circuit Playground. But there's also some other non-Adafruit boards, I think, that are supported by CircuitPython. And there's a lot of them. So let me show you what happens, how it works. Since I was showing my desktop, I think I can do this. I'll go ahead and clear some space off here. My desktop is like super messy, so this is going to be ugly. But I'm going to plug in this CPX, which probably already has some code on it. Somebody left some code on there. And it'll start running, I presume. Okay, some program's running on there. But what happened is, and my Zoom window is right in the way, but I'll get it down. Hang on. If you see here, if you can see my mouse pointer, see the circuit, can you see the CircuitPy disk icon on the Mac? Same thing works on Windows, it just looks a little different. If you open that drive, it has a few files. One is code.py, which is actually the code that's running right now to flash the LEDs on this CPX. And that's Python code. And they just basically create it in any editor you want, call it anything you want, drag it over to the CircuitPython board and drop it, in the case of the Mac, on CircuitPython drive, CircuitPy drive, and then rename it code.py. It auto-magically reboots and your code starts running. You want to see the code that's on there, you can, again, you can use any editor. Let's just open it with Visual Studio Code. And let me get this thing out of the way. My Zoom gauge out of the way. Not sure where I got this program from. I'm not sure if I put it on here, but obviously this is CircuitPython. And because I'm using Visual Studio Code, I get the syntax coloring and probably the IntelliSense functionality and all that kind of stuff. So in that sense, they've done a very smooth and very easy integration. This in particular, they have a lot of built-in methods for dealing with the peripherals that you find on the CPX, because it's got a bunch of built-in peripherals, right? It's got neopixels, which are the lights that are flashing. It's got a temperature sensor. It's got a sound sensor. It's got a speaker. It's got, I have to look at the board, 2 switches, a slide switch, and some other goodies. So they've actually got, of course, Python modules to help you talk to those peripherals. So the easiest way to start out with a Python on embedded microcontrollers, I believe, is to use CircuitPython and use it with an Adafruit board, whether the CPX or another one. I actually like CPX. I use them in my classes sometimes because you don't need a breadboard with a bunch of wires running all over the place that make you feel like a hardware person, because a lot of the peripherals that you like to make some interesting apps are integrated on the board. So it's kind of got a high degree of integration. That's not true of, say, the ESP32, which is just a microcontroller and which requires a board and peripherals that you add yourself if you want to get LEDs or LCD displays or anything like that. So basically, that's what CircuitPython looks like. And to me, the biggest difference, I'm not actually aware of all the niceties of feature differences, although there's a page I'll point you to, which does go through all that. Here, MicroPython versus CircuitPython, and I can drop some of these in the chat if you want, but basically, let's see if there's a list of differences. Okay, here's some differences. The includes a port to the SAM-D21. That's basically an ARM M0. So the MicroPython, I don't know if it's got an ARM port or not. It may have, because the two chase one another along, right? MicroPython makes an update. CircuitPython generally accepts that feature. Right now, CircuitPython appears to be only available, if this page is correct, on Adafruit's ARM machines. That's the SAM ones. I think that's what Atmel calls the ARM processors they sell. And the 8266, which is the forerunner of the ESP32. That's the super inexpensive, like $5 Chinese-made Wi-Fi capable microcontroller. The ESP32 is the $8, much larger Wi-Fi capable Chinese-made microcontroller. There's some differences in int sizes. If you're using long ints on there, I mean, I'm not sure that that's a memory constraint, right? It's just, so not very many big differences. The big differences will come, as you'll see, when we look at how we address the board, how you actually get code onto the board, and how you talk to the board. So any questions so far? Okay, I'll cut to MicroPython. MicroPython is a really complete implementation of Python. They're showing you here, the picture is showing you, by the way, that's an ESP32. That's the, its claim to fame is it is some kind of custom core. No one seems to know quite what it is. I thought it was ARM, but it isn't just ARM. It's a Chinese-made core that has built-in Wi-Fi. So it has two cores, one of which is pretty much dedicated to running a Wi-Fi connection, and one of which is available for applications. It's also running internally a little RTOS. I think it's running, I think it is running RTOS to enable it to task switch between your code and the Wi-Fi. The real advantage over the 8266, besides the fact it's faster and has more memory, is that the Wi-Fi works a lot better because you can't kill your Wi-Fi connection by hanging up your Python code in your application, because there's a separate processor that's time sliced to keep your Wi-Fi connection up. So that gets rid of one of the main complaints about the 8266. If we go down to this is the specific to the port for the 8266. And there are, when you see these machine dot, those are particular modules that are customized for this machine, right? And the ESP dot, again, those are hardware specific modules in MicroPython that talk to the ESP board in this case. So there are a number of those. Of course, those aren't necessarily in CircuitPython, nor are any of the SAM-D specific stuff in MicroPython. Networking works pretty well. I'll show you in a second how you can get the board on the Wi-Fi, and it will connect to your Wi-Fi and run. I have a little web server running on this board, which I see I just knocked a wire loose on. So this will be live hardware. If you like live coding, you'll like live hardware even better. And you can see there's a long list of functions, including capacitive touch, which is on the CPX. We're going to be using the Dht driver. I don't know what Dht stands for, but it's a temperature and humidity sensor. Extremely common, inexpensive temperature and humidity sensor. I'm using that. WebREPL, that lets you get an REPL prompt across the Wi-Fi if you want. So you could actually sit in your easy chair and play in the REPL on your ESP32 across the room, if that makes sense to you. Mine is connected by USB cable, but it could be Wi-Fi. And there's a usual set of functions one would expect in a microcontroller, meaning timers, pulse width modulation, analog to digital, SPI, so forth and so on. I'm actually using the SPI bus in this on the board, as you'll see. So let's go ahead and look at some code that's actually running on the board. Now this is running in Visual Studio Code. And I mean, I really like VS Code. I did have to say, I wanted to, for this presentation, trace out neatly for you all the steps I did to get this working, but I got lost. I installed a boatload of extensions. And I honestly would have to reverse engineer it to figure out exactly, and then I uninstalled exactly which ones. However, the main one that I'm using is something called PyMaker, P-Y-M-A-K-R. That's the section that automates a couple of useful things. Well, there's several extensions. One extension here lets you use essentially Intellisense, Visual Studio Code's Intellisense. That's the basically linting and syntax highlighting that goes on in Visual Studio Code. It lets you use that even though your processor is just connected by a USB cable. So they kind of cheat and they make sort of local copies of the Python modules you install. They call them stubs. And they use the stubs to drive the Visual Studio Code Intellisense highlighting. So if I go and let's get, this is the one on the CPX. Let's get the one for main. You can see already I'm in trouble with Intellisense. The lint, PyLint actually. It ranges, the PyLint, you know, ranges from trivial to profound. It finds a lot of errors, and it also whines about like extra white space. Yeah. But it's, all in all, it's very handy. And with PyMaker installed, that's, you get a series of commands that allow you to talk to the board when it's plugged in. So I'm going to unplug the CPX. I'm going to plug in, I'll fix my wire first of all. I hope that's the right place. We'll find out. And plug this guy in so he's powered up. Should see some red power lights. The red light over here is under program control. It'll turn green when I connect to the Wi-Fi. So I just basically, I'll show you the code. I wait until I get a Wi-Fi connect. Right now it's trying to connect to my phone, which my hotspot's turned off, so it's gonna take a while. Eventually it'll give up on the phone and it'll connect to my home Wi-Fi, I hope, and it should go green. Always seems to take a very long time when, there we go, it's green. So this LCD display on here is an inexpensive, and of course it failed to read the sensor the first time. I don't know if you can read this text on here. It doesn't do well on camera. It's pretty easy to read if you're there, but basically it should come up with the time and temp. There we go. Time and temp every minute or so. Looks like heck on this camera, but and it's also, oops, I just lost my, another hardware problem. Anyway, I just lost my power connection. But basically, if I had soldered the wire on the way I should have in my haste, this would be working better. There's also a little web server running on here. Again, this is Python module I found that I just tinkered with and got it to work. So first I'm going to connect. So the connect just basically says, go out on the USB bus and look for the serial device that represents the ESP32. And that calls itself on the Mac, slab USB to UART, blah, 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 right? It's a serial, high-speed serial connection. Having done that, any code changes I make here, I can then push over into the ESP32 and it'll reboot and run them. So let's make some kind of small change here, like, I don't know, we'll turn the backlight off, maybe. Save that, and down here, actually even a shortcut for this one. Let's see, this should cause it to, so I'll try to hold it so you can see it. And I'll upload the code. It's smart enough to know I only changed one file, so it only uploads the one file. The chip reboots, so all the messages you see now on screen share are from the ESP32 booting up. And my boot up message will appear in a minute or two. And, okay, I'm on the network because this says network config. That's my IP address. I'm at .144. So I'm on the network. And if I actually go to here and reload the page. Yep. So I've got the temperature and humidity. It's a very stupid web server now, as you'll see. But it does, you know, if you just want to get the temperature and humidity in your garage from your living room, it works fine. Right? Not a very robust web server. If you want, I can walk through some of the code. I think the Python code is sort of interesting. Not hearing any nays, I'll walk through some of the code. The boot.py is it's like the code.py in the CPX. You had to name your Python file code.py if you wanted it to run automatically. Boot.py is any file called boot.py is automatically run when the ESP32 reboots. So that's usually where you set up connections to Wi-Fi if you need. So I just took the connection code that I found in the examples on the MicroPython page and adapted it so that it could try more than one access point. Because one of the bane of my existence was a lot of microcontrollers was in trying to demo them. If I set them up to connect to my home Wi-Fi, I couldn't demo them. If I set them up to connect to my phone, if my phone wasn't, hotspot wasn't on, it wouldn't work. So I made a collection, small list of Wi-Fi access points and their credentials. And this code just cycles through it until it either gets a connection or gives up. So that's why the initial delay, the light's red for a while, it's trying to connect to my phone first. So that code here comes from the network module, which again is probably an ESP32 module, I think, at the top. It has a separate module, network and ESP32. So most of this code is straight out of their example. Easy to do. And it seems to work pretty well. Config.py has some data, including my password and so forth, so I'll skip that one. It's ABC123 if you need to know. Yeah, just like on my phone. No, my phone is 1234. Sorry, I get those confused. This is actually code that I tinker with. This one's interesting. This is a CircuitPython piece of code that I tinkered around to work in MicroPython, because CircuitPython had a driver for this LCD. I turned the backlight off, so it probably looks pretty dumb, but MicroPython did not have a driver for that LCD, because that LCD is also connected to a little board here. LCDs normally are essentially parallel devices. They want a boatload of pins, which you probably don't want to do because you can't do anything else but talk to the LCD. This is a little, essentially SPI to parallel converter that enables this LCD to appear as if it were an SPI device. So it only needs 3 pins. So that's that code. I couldn't find it for MicroPython, but I found it for CircuitPython. That's why the CP here. So I didn't need to make very many changes to make it work with MicroPython. The changes I had to make were the way they addressed, oh, it's I2C, not SPI, I'm sorry. Those two high-speed synchronous serial protocols are really rather similar. And I get them confused. But basically, they're like the write to method here, it was called send. And some of the other ones had different names, or took slightly different parameters. But it was really like about maybe a half hour's work to bring this back from CircuitPython into where it would work with MicroPython. The HAL ones are the hardware dependent. They did a good job, actually. This is all the hardware dependent stuff. And this module, which has an error, which is not really an error. The linter got a little bit carried away. But this is the one that actually provides the API. So basically, you subclass this. I'll get the top here. You subclass this and get with a hardware specific version that then fills in all of these HAL methods that are essentially, I don't know what the Python term is, they're basically virtual. They're like virtual methods in C++. They're not really there, or abstract methods. So that was interesting. So that's how close CircuitPython and MicroPython are. When one is a little bit ahead of the other, it's really not too hard to convert between them. I merely made mostly spelling changes to get this code to work. LED.py is the module I put together to turn which is overkill to try to turn the LEDs on and off in a cool way. Maybe that would have been better just to do that in line. Main.py is where we started, and that's the main down here, which is the run forever loop that every embedded program has. This I2C here that's how you actually get a an object of class I2C, which knows how to speak to that LCD converter. So you tell it which pins to use, what frequency to use, and you get back an object which you can then use to talk to the LCD. So then the LCD is based on, it's an instance of this I2C LCD, which uses this connection essentially. So the DHT stuff here is the, that's the temperature and humidity sensor. That's this thing, if you can see it, if I can find out. Watch me hold it in front of my picture. This little guy, they're like $5 on Amazon or something. And they work really pretty well if you have all the wires hooked up. And so this encapsulates talking to that. I don't know what magic's going on there, but I didn't have to know. I imported a Python module that knows how to do that, right? And I just instantiate a sensor object, and there we go. Print a welcome message, which I just basically say, you know, MicroPython, and I think I read the CPU temperature just because it's one of those things that you might not care about, but it's always there, so it gives you something to do. It's a good sanity test. Then I connect to the Wi-Fi. So I do that repeated, can I get on the phone? No. Can I get on the home Wi-Fi? Yes. And I guess if you get here, a bad thing happened. Then I start the little web server up, which I'll show you in a minute. And then forever, basically take 2 seconds to wait for web requests. I told you this is pretty simple-minded. And then turn around, deal with anything you get, turn around and read the time and the temperature and humidity, put them up on a display, go back around and wait for web requests for 2 seconds. I tried to get this to work with coroutines. I tried to get it to work with, then I tried async IO, and I wasn't able to get it to work before I got too frustrated. So I lapsed into the ancient design pattern for embedded code, which is essentially the super loop, right? It's just basically a polling loop. And that will always work, but if you try to do very much in a polling loop, it gets out of control very quickly. And of course, various forms of threading or coroutines make that a lot cleaner if you have a lot of tasks to do. If you only have 2 tasks, just look for a web request and read the temperature. It works pretty well. So, and the web server modules here, again, I plagiarized this heavily from the MicroPython examples. I'm also terrible in HTML, so I just copy and paste HTML from WW3 schools, and I hack it up until it sort of displays, and then I go on about my business. So I made it in 2 pieces. Yes, there are more elegant ways to do this, so I could splice in the temperature and humidity numbers. I know there's a lot better ways to do that with string substitution. And then here, essentially, I get a non-blocking socket. Normally, if you open a listening socket for a TCP/IP connection, execution stops until someone connects on that socket. And then you do an accept, which says, okay, let's move off of the well-known socket like 80 to some other anonymous port to do our interchange. That's how all web servers really are, simple ones are architected. You can also open what's called a non-blocking socket. Let's see if I can see where that is. Yeah, self.sock.setBlockingFalse, which is really like just basically runs in a loop, polling the socket. Do you have anything for me? Do you have anything for me? Do you have anything for me? Until the time runs, either you get a request or time runs out. You can tell it how long to wait, telling it 2 seconds. If it does get something, it's going to do this. The uSelect poll is what actually drives that checking. It's going to accept the connection down here, throw out a message, put my butchered HTML together into one big chunk of HTML, and send it off. So that's essentially the whole program. And yeah, you could do this in C, C++ quite easily. It's a lot easier, I think, in Python. It's a lot more fun, and it's a lot easier to understand. Socket code in C is particularly twisted. And so that's basically, so you got 2 options, good options for embedded Python. CircuitPython if you want with Adafruit stuff, if you want the drag and drop modality and kind of the DIY angle, and the Visual Studio Code plus 8 bazillion extensions if you have, you know, more hardcore embedded hardware and you want maybe a more, I hate to say professional, but maybe a more professional development environment. So that's basically it. Questions? I want to share my, well, wait.
I can get the questions. Oh, actually, let's start with the text. So we have in the chat, how many of the library, or do you know of any libraries for erasing the usage of LED matrices?
Okay, I looked at LED matrix drivers. The problem there is, of course, there are many different LED matrices and they use different driver chips. The small ones that are done with the Max 7.2 something or other, the driver is available in MicroPython and CircuitPython. So you can just basically say, I have a matrix of this many elements and I want to bit address it or whatever.
Sorry, I misspoke on that. It's for easing the usage.
Okay, same thing. Yeah, there's a couple of libraries, and actually, let's look at one. I started down this road. I would really like to connect one of those to one of these boards, but I didn't get that far yet. I've done it in C. I have a number of examples of talking to those guys in C, and many of the libraries to do that are done in C. But I think there's a Python wrapper for some of them that would enable you to use the library without having to re-implement it. A lot of them are in C because as far as I know, all of those matrix displays are serial, basically. They're big shift registers. You shift bits in and those bits are moved to particular pixels and they turn on or off or change the color of particular pixels. You have to do that pretty fast if you want, say, animation, like fast scrolling text or, and that drives you back towards C pretty quickly because Python is not nearly, in that kind of environment, it's not nearly as quick. If you just want to display messages and walk the text across the screen, I'm sure Python is plenty fast enough. Let me see if I can find a library quickly. Here's the story. I had to reboot right before this because Zoom decided it didn't like my microphone anymore. So all of the windows that I had opened that I intended to talk about all disappeared, and I'm not sure that I have recreated them all, but I think I bookmarked. Here's one. This is a MicroPython driver for the Max 7219. Now that's the chip number, right? That's the chip on the back of the display, or actually multiple ones of them, that's responsible for actually shifting the bits along and illuminating the pixels. And here, the 8x8 LED matrices, which is a little block about the size of a big postage stamp. I don't have one in this room, but I have a bunch of them. They're really easy to program. And they basically speak SPI, which is a high-speed serial interface. So you only need like 4 wires. And you can daisy chain them together and get longer displays. So any of those looks like we've got, pretty good Python support for. For the larger displays, I don't know if those chips are yet supported in MicroPython. I was going to investigate that and I haven't gotten that far yet. This Max 7219 is so commonly used, that's why the support's there, right? It's used in a lot of boards. You have to look at the boards and see what, when you're browsing Amazon, and see if you can figure out what driver chips they actually use based on the reviews and whatever answered questions the vendor may have deigned to answer. So I don't know if I answered your question, but yeah, there's definitely some MicroPython support for some matrix displays, but I don't know if particular ones are supported or not, particularly the larger ones.
I see that he did specify the WS28012B, which is the pre-2018 NeoPixel brand before they switched over to the 13. Okay. It would be, I'm not, how well would the Max 7219 library work with a different LED chipset?
I think, well, I mean, it's on the board, so presumably it does in some sense work with the chips that are there, right? Because you're not generally adding that board on. Usually they come as an integral unit. Well, it's not true. There's for the let me find what I'll show you. Let's shop Amazon for a minute, and I'll show you one type that I have spent a fair amount of time with. Smaller displays. Let me see if I can get cancel this. You'd see my whole Amazon account here. Super secret stuff. Where's some stuff I bought lately? I bought one the other day. Wonderful stuff. Let's see. Here we go. The Dioki Max 7219 dot LED matrix. These are monocolor. So in other words, they're not actually neopixels. You can't actually pick the color of the pixel. You pick the color of the display, and you can pick red, green, or blue. Red is $6, green is $9, and blue is $12. I'm not sure why. And that's actually 4 8x, I'm pointing at the screen for all the good it will do you, 4 8x8 modules daisy chained together to make a 32x8 display. That's driven, each of those, if you look carefully here, you'll see there's a daughter board, there's a motherboard, and these modules are plugged into it. The modules are just LEDs. You can actually unplug them and plug in maybe a different color. So if you wanted to have alternate panels be different colors. The driver chip is on the motherboard. The driver chip there is one or more 7219s. And so if you have code that knows how to send data to a 7219, it will probably work with these, but there are variations. When you look in the library for the Max 7219, at least in C, and I think it's probably true in Python also, you select what particular species of LED matrix you have. If you select the wrong one, your display will be upside down, or your characters will be mirror imaged, or some other odd artifacts that have to do with the way the motherboard itself is wired between the chip, the 7219 that's getting the data, and the actual LEDs. But I was able to find a combination that worked for these particular boards. Again, I have not tried it with MicroPython yet. I have it running with C. And that was my next step was, okay, let's see if I can get this to run for just one of these 32x8s using MicroPython. And I hope so. I'll let you know when I figure out.
Yeah, I'm looking in the chat here, posted again. The specific project is uploading GIFs to a web server. So similar to what you have running on the ESP32 there, it actually mentions ESP32 specifically. And then having the board take that image and display it onto an LED matrix. Presumably, it maybe one of those 8x8 or tiled 8x8.
They make much larger ones. I've got
some that they make.
I've got some at school that are, well, they're locked up now. When I get my hands on them, they're, I think, 128 by 64 maybe. And they actually have multiple colors. And those guys can be, I know they can be run with an ESP32, but all the code I've seen to do that has been in C. So I don't know what, I've not yet figured out what MicroPython code is available for that. The basic architecture would be to have a web server. That part is easy in MicroPython that accepts requests, post requests or something, or gets, doesn't matter. Make your own little RESTful API, which then accepts the text you want to display and displays it. But I'm not sure what, if the right drivers are available for MicroPython or not. I just don't know. For the big ones. They are for the small ones, I'm pretty sure.
I'd say that this isn't a library thing, but I think just being able to accept the images there, you'd have memory and then sampling or scaling issues just to figure out what all the colors should be in the first place.
Yes, I was assuming you sent it pretty much pre-processed images because, yeah, there's not a lot of bandwidth to do. If you want to do that, you might, maybe that's like the Raspberry Pi class machine is closer to the horsepower that you would need. And of course you could run over regular Python on a Raspberry Pi. And that might be a better scheme for driving. And a Raspberry Pi can talk SPI and I2C, the serial protocols that are used to interface to LED matrices. So that might be a better architecture and it wouldn't be really much more expensive.
Yeah, and
Raspberry Pi Zero is going.
the new the Gen 4 Raspberry Pis all have Wi-Fi built into the chip, and you can even get away with the not the embedded, but the Zero, the Pi Zero for
Yep.
$5 to drive the
Yeah.
same displays.
I love the Zeros. They're cute little boxes, and they're so inexpensive. You can really use them like a microcontroller almost. The only drawback I see to an embedded application is something like a Pi Zero, assuming your app is not too demanding, is that you have to be careful in the startup and shutdown, right? Because it's a true Linux box with a file system on a micro SD card. You can't just pull the plug and walk over to the next outlet and plug it in too many times. And, you know, you do that enough times, sooner or later, it's going to corrupt the micro SD card. The beauty of everything in Flash world here is that I can just unplug this and plug it right back in, and it just starts up and runs, right? There's nothing to get corrupted. So, but other than that, having to be careful about startup and shutdown, the Pi Zero for low end stuff is a great little machine, and the Pi 4s have gotten, I don't know, 8 gig of memory now, and I don't know, gigahertz at least, clock speed maybe 2. They're becoming really impressive. And you can run full-fledged Python. You don't have to worry about running out of memory much. I mean, you always have to worry about running out of memory, but not on the same scale. And they're pretty performant.
So I have a question. I've run into this a handful of times when I've been doing CircuitPython, and I'm sure I'm not quite sure how relatable this is to MicroPython as well. But dealing with the third-party dependencies, I know with CircuitPython there is that giant download of all of the compiled third-party libraries you have on there. But when I've gone to update the bootloader, or to take the bootloader and update the version of CircuitPython that is running, needing to get the third-party libraries back on there, just the minimal amount. I wonder if there's any tips or any kind of tool that you have that makes that easier to manage, because it's even just getting it back to a workable state, like with the CPX, just getting the CPX library on there, you then have to go on a wild goose chase to figure out all of its dependencies as well that are not included.
I don't know for CircuitPython, honestly. I do think that for the MicroPython, using Visual Studio Code and the correct extensions here, that some of that's automated for you, because the way this works is that if I need to install a module I don't have now on the ESP32, I don't just use a regular pip install. I use a special install program in the terminal that installs it 2 places. It copies it over into the ESP32. It also sets up these stubs that enable you to have a GUI interface on this side of the wire. I think it's also possible to pre-compile stuff and upload it, but I haven't tried that. I'll reveal my ignorance of Python because it's pretty vast. What are PYI files? I see a bunch of those.
I know that the compiled libraries for CircuitPython at least are the .mpys.
Okay, so PYI, I don't know, maybe this is one of their stubs. It's an odd looking thing. It looks like it's just, if it were C, you'd say it's prototypes.
Yeah, this looks like a stub.
Yeah, that's the stub. So it does that. You can create MPYs, I think, and upload them, but I haven't tried that yet. That would, because this has a kind of make-like functionality on one of the extensions, it knows what you've changed. I think it would be intelligent enough to upload all your dependencies, but that's something you'd have to try. Because here you actually have code working for you in the upload, code looking at what's changed, make-like, looking at what's changed. And I think you're more on your own on CircuitPython to move stuff over. But you're right. There's a big bundle of files which they warn you, don't try to put all this on your on your CPX. It won't fit, which is true because it's like the entire Python library. You have to pick and choose. But yeah, it's kind of painful. I think it would be less painful here because I believe here, if I take out a needed module, the dependency that's not here, I should get, I think, a bunch of warnings. I took out one I wasn't using, which was smart. Here we go. Undefined variable ESP because it wasn't imported. So you might, I don't know, it might catch some stuff, some missing dependencies over here. I don't know.
I had a similar question. So this is the first time I've ever seen MicroPython, and it's a subset of the full standard library. Were there any points that you hit commonly that, you know, something that they didn't include in their version that kind of comes up more often than not?
I haven't, but then my utilization of this has been pretty limited. This is the first major piece of MicroPython that I've written. However, there's a web page that I think I'd opened, but I may have lost it. But very quickly, there's a MicroPython, I think CPython is what they compare themselves to. And I'm thinking that's the canonical Python. I'm not sure. But there's a list. Let's see if the list shows us anything we think.
Yeah, I don't think the C doesn't stand for anything. It's just the fact that Python runs on C. So CPython is just the one that is maintained by the core developers.
Not to be confused with Python, right?
Not to be confused with Python.
Yeah, so let's just pick one JSON. So yeah, the CircuitPython output, CPython output, type error, MicroPython errors should not get here. That suggests that maybe it's a little bit dicey there. But again, it has a lot to do with the app. You're probably not, hopefully not, trying to write applications in a MicroPython environment that use modules like, I don't know, pandas or something that's probably a real memory consumer, let's not say hog.
Right.
And I think that kind of thing you're definitely going to run into. But
no, I was just thinking.
Core,
I was just saying. I was thinking in the terms of when you're talking about the dependencies. The dependencies might expect that it's running on a normal Python install, but I'm just curious if that's a common pain point that the dependency you might want to add is missing something that's fairly common, like OS. Import OS.
Let's consider the Bible here, which is Stack Overflow. That's no link though. 2013 is, that could very well be, yeah. No, that's a worthless link. The answer is I don't know. Unfortunately, I haven't done it enough to know where the pain points are. I'm sure I'll find them.
Okay. Yeah, I was just curious if you had run into them already.
I would not attempt to run anything using async IO on an embedded program though.
I tried that and it didn't work. I tried it on the spot. I tried to make async IO, make my web server and my temperature thing play nice, and I couldn't get it together. Part of that was me, of course.
And I was going to say another question. I know you're a Java guy. Have you done anything with like Java ME, and is there any comparison to how you're doing it in MicroPython?
Really not. I'm really not a Java guy, and I'm a C++ guy originally. I used to try to get I used to try to get Java on microcontrollers because I was teaching Java, and that seemed to me like a lot more interesting environment than just sitting there in Clips writing PC apps. But most of at the time, this is a number of years ago, I tried it. Most microcontrollers were not up to even hardly running the JRE. Let alone if you wanted to try to develop on the machine or something. I mean, because there's really two levels, right? There's cross development, which is in which you develop on your PC and you download presumably Java bytecode to the JRE, which lives on the microcontroller. Right. And then there's like a Raspberry Pi, or if you want, particularly on a 4, you could probably install Eclipse and do your development on the box. But I was having trouble finding controllers. And they were doing awful workarounds like special subsets and special, you could use some Java features and not others, and it was terrible. It may have gotten better, but I really think Java on, which is ironic, that Java on embedded devices has kind of reached a dead end. I say it's ironic because, as I understand the history of Java, it was originally intended as a language for set-top boxes, which is one of the first big embedded applications.
Yeah, they were trying to put it on credit cards. What am I trying to say? Like the smart cards.
Yeah.
Like it would fit in. I think it was either 16 or 64K. I don't mean to derail this into a Java conversation. I was just curious if you had, again, insight between the Java ME and MicroPython.
I haven't looked recently, as I say, because I'm just not a big fan of Java, except as a teaching language. I think it's a great teaching language. And I think C is a terrible teaching language, and I teach multiple courses in C. So.
Brun posted something interesting in the chat that presumably he's tried before, called the Pixel Blaze, which is just a Tindy board.
Okay.
Is run the Wi-Fi compatible, so it's running in ESP32 as well. But it comes with code on it to have a web interface for programming your LED strips, and it works with dot stars and NeoPixels. Primarily accepts either JavaScript or C-like syntax. So no Python, but interesting.
Yeah, it is, actually. There's a lot of interest in the LED matrices because they're so widely used. Well, the giant ones, of course, are used on all kinds of signage. I think that may be driving some of the interest in the smaller ones. And I have folks who want to build like little wearables and stuff out of them. So kind of the other end of the spectrum from the giant scoreboards.
And it's crazy that if you want, you can do so much with microcontrollers and these generally cheap controllers with all these the matrices and all the LED strips to do so much. The next step up above these are enterprise systems that cost thousands of dollars.
It doesn't seem to be a middle ground. When I was looking on Amazon for LED panels, you just put in LED panel and start browsing through the Amazon hits. They run from little 8x8 ones that I saw up these things that are $5,000 a pop. And I think you need multiples of them, which you then assemble together to make even, like Legos, to make even larger displays, right? They're, still price is still up there for the big ones. No doubt about that. And I guess blue displays are more expensive than red displays because blue LEDs cost more than red LEDs. I honestly don't know.
And I would imagine that the compound, the chemical compound that they use in the LED would be more expensive to be blue. And I think the history of LEDs, blue was the last one to be created because they couldn't find a good compound for it. I love the physics of LEDs, is describing them as heat rockets. Whereas if you have an incandescent bulb and most resistant-based light sources, the heat radiates out in all directions, the same as where the light gets pointed towards. But with LEDs, it separates the two, so all of the light coming out of an LED shoots off in one direction, and all the heat gets shot out the exact opposite direction.
That's why they're glued to a big heat sink, I guess. That makes sense.
Yep.
The larger fixtures, they're all glued to like a metal strip. And they even have the COB, chip on board, which is basically one big LED. It's not little LEDs tied together. It's one big LED on a metal strip, which serves as a heat sink.
Yeah, and I don't know how many people are familiar with theatrical and entertainment-based lighting devices, but in the not too recent past, you would have these incandescent bulbs that were insanely bright, about yay big, including that giant connector that you put it in there, you clamp it down. But if you had to be very careful with these bulbs, because if your finger touched the actual glass part of the bulbs, these things burn so hot that over time, the oil that came off of your finger onto the glass would cause it to bubble out and decrease the lifespan of this bulb by well, I guess hours, because they only last so long. They don't exactly last years. But
That's still
the industry as a whole has moved away from all of those to being it's very hard to find a non-LED entertainment lighting device of one kind or another, just because they're using, they finally get the same amount of brightness as they have those old style incandescent, high throughput incandescent bulbs, but while they are still producing huge, orders of magnitude less heat.
Yes.
They're still producing so much heat because it's all getting concentrated back into the device itself.
But they end up consuming much less power. And you're right. Even now, if you look at a halogen headlight for your car, it says when installing it, don't put your fingers on the tube, because that same thing you were saying about it actually weakens the glass. So the halogen lights have I think some gas in there that increases their brightness. Or I'm no chemist. I'm way over my knowledge of chemistry now, but yeah. And of course, in the good old days, and this is before my time, I would quickly emphasize, they had arc lights, which were where you actually had an electrical discharge between two consumable electrodes, and it made a light so bright that it was used in spotlights. Used in anti-aircraft lighting. In World War II, and there may still be a few around for circuses or something. I don't know.
Thank you, Gerry.
Oh, well, thank you guys for listening.
Thank you so much, Gerry.
I love talking about this stuff, and I'm still learning it. I've still got a lot of MicroPython stuff I haven't learned, but I'm going to go in this direction, I think. For a while.
It looks cool, working with all these LEDs and gizmos.
Oh, I love LEDs.
Yeah.
You can't see in this camera here, but behind camera, is I don't know if you can see that. Oh, maybe. I've got a strip of 144 LEDs on a strip of wood that I'm working on for another project, and I just have a program that runs the LED up and down. It's a lot of fun. It drives cats crazy too. But